This is the first lecture in our course on numerical methods in civil engineering. In the first lecture, I am going to talk about Introduction to Numerical Methods. Before going into further details, I would like to mention two references which I am going to follow throughout this course. The first reference is Numerical Methods by Dahlquist and Borg. The second reference is Methods of Applied Mathematics by Hildebrand. First, I would like to talk about why it is necessary to do mathematical modeling. We use numerical methods in civil engineering to solve mathematical models of civil engineering problems. Examples of such mathematical models are many and cover every discipline encompassed by civil engineering. For instance, in structural engineering, we need models to accurately analyze three-dimensional structural frames. In geotechnical engineering, we need models to understand liquefaction of soil during earthquakes. Transportation engineering, for instance, we use traffic flow models for optimized traffic movement. In environmental engineering, we use models to study the percolation of contaminants into groundwater. And in hydraulics and water resources engineering, we use models that capture the complex flow patterns past locks and weirs. The need for numerical methods to study civil engineering problems is best understood by considering a typical problem. Since I am a structural engineer, I will choose a typical problem from the field of structural engineering. Suppose we have a factory housing sensitive equipment located next to a railway line, and the railway authorities plan to upgrade the line to allow for high-speed urban commuter rail. During the planning phase, they face representations from the factory owner that the planned high-speed rail traffic is going to cause unacceptable levels of vibrations to the factory floor, severely affecting the usage of the equipment. The structural engineering consultants whom the railway authorities employ to test whether the objection is valid decide to analyze the vibrations of the factory floor slab. To do this, they decide to set up a mathematical model of the floor subject to the motions expected from the passage of the high-speed train. Since the thickness of the floor is relatively small compared to its length and width, they model the floor as a thin plate. Then they try to solve a problem typical in structural engineering, the flexural vibrations of a thin plate due to the excitation from the train traffic, to see if the magnitudes of the vibrations exceed tolerable limits. In modeling the floor as a thin plate, the analysts make certain assumptions or idealizations. Such idealizations simplify the mathematical modeling of a problem and allow us to solve it using the tools at our command. It is perfectly fine to make such simplifying assumptions or idealizations so long as they satisfy two conditions. First, despite them, the modeler is able to capture the physics of the problem up to an acceptable level of accuracy. 2. The modeler is fully aware of the restrictions the idealizations impose on the range of applicability of the mathematical model. In modeling the floor slab as a thin plate, in addition to the thin assumption, we make two further important assumptions regarding the mechanical behavior of the floor. First, the rotations of the floor are insignificant compared to the vertical translations. 2. The shear deformations of the floor is small in relation to the bending deformations. These assumptions allow the response of the plate to be measured in terms of its vertical translations W, which although varying from point to point along the length and width of the plate, does not vary significantly through the thickness of the thin plate. The mathematical model can then be written in terms of the vertical translations W as a function of the planar coordinates x, y and time t. Thus, W, where W is a function of x, y and t, satisfies the following equation which governs the flexural vibrations of thin plates. To summarize then, to get physically accurate results from an analytical model, we have to 1. Make reasonable assumptions about the physics, which phenomena are important and which are not, what is the type and range of behavior we are interested in modeling, etc. Given the assumptions, set up a mathematical model that best represents the phenomena. Finally, make sure that the model is not applied to predict behavior outside its feasibility region. For instance, the above model for the floor vibrations is not valid if the floor is undergoing finite rotations or in situations where the transverse shear deformations of the floor are important. However, sometimes even if the above conditions are satisfied, we cannot solve our model using the mathematical tools at our command, or the analytical solutions are too complex and time-consuming to be of practical use for most engineers. For instance, in the floor vibration problem, if either of the following is true, either the thickness of the floor is an arbitrary function of the planar coordinates x and y, the elastic modulus is an arbitrary function of the planar coordinates x and y, the elastic modulus is a function of the deformation, that is E is a function of the solution W, the boundaries of the floor are arbitrarily shaped, or the floors have complex cutouts, the problem becomes too complicated to solve using the analytical methods a civil engineer has at his command. In such situations, the problem can only be solved through the use of numerical methods. The complications enumerated above are instances of A. Complex geometry, geometrical and material nonlinearities. Two typical scenarios where numerical methods find application in solving otherwise intractable analytical models of civil engineering problems. For instance, for the floor vibration problem, the consultants will probably use either the finite element or finite difference method, two popular numerical techniques for solving partial differential equations to solve their problem. Before starting to talk in any detail about numerical methods in particular, it is appropriate at this stage to make a distinction between a numerical method and a numerical algorithm. Given the mathematical description of a problem, a numerical method lays down the broad approach to be adopted to solve the problem numerically. For instance, for the floor vibration problem, if we wish to use the finite difference method, we would begin by writing the finite difference form, which is an approximation of the derivatives appearing in the governing differential equation. On the other hand, if we wish to use the finite element method, we would start with trying to construct finite dimensional trial and test functions to approximate the exact solution W of the above problem. Once we have chosen a numerical method, There are a wide variety of algorithms we can choose to do a step-by-step implementation of the chosen numerical method. A finite element implementation, for instance, may adopt an explicit or implicit algorithm to solve the governing equation. The implementation of these two algorithms are widely different despite our choice of the same numerical method, that is, the finite element method. An implicit algorithm is unconditionally stable, but for strongly nonlinear problems may encounter convergence difficulties. An explicit algorithm, on the other hand, is conditionally stable, that is, it is stable only if the load increments are less than a certain limiting value. However, they do not encounter convergence problems. Next, we would like to look at certain concepts that are common to most numerical methods. The first concept that we wish to examine is the idea of iteration. It refers to repeated application of a numerical process in order to successively improve previous results. Consider the solution of the equation x is equal to f of x, where f of x is a differentiable function with continuous derivatives whose value can be computed for any value of x within a certain interval. We start with an initial approximation and compute the sequence. We start with the initial approximation x0, and substituting x0 in the expression for f of x, we compute the value x1. We use the new value x1 again in the equation for fx to come up with the next iterate x2, and so on and so forth until we get f of xn minus 1, which is equal to xn. If the sequence xn converges to a limiting value alpha, then alpha satisfies the equation and limiting value of f of xn is equal to f of alpha. So alpha is the root of this equation. As the number of iterations n grows, it is desirable that xn be a better and better estimate of the desired root, and the iterations be stopped when sufficient accuracy has been attained. However, it is not always assured that the iterations will converge. As the following figure shows, the iterations converge in only the first 2 of the 4 cases shown below. We start with an initial assumption, and in case 1 and case 2, we converge to the true solution, which is where the blue curve intersects the red curve, right? In case 3 and 4, we can see that even if we start near this true solution, our iteration process takes us away from the root or the true solution. In case 1 and case 2, the solution becomes closer and closer to the root as n increases, while in cases 3 and 4, the solution moves farther and farther away from the root as n increases. The reason for this is clear from the following. From the iteration algorithm, we can write xn plus 1 minus xn is equal to f of xn minus f of xn minus 1. Recall that according to our algorithm, xn plus 1 is equal to f of xn and xn is equal to f of xn minus 1. Dividing both sides by xn minus 1, we get the following. But using the mean value theorem, we can write fxn minus f of xn minus 1 is equal to xn minus xn minus 1 times the derivative of f evaluated at a value xi, where xi lies in the interval xn minus 1 and xn. Thus, looking at the last equation, it is clear that convergence is faster, that is, the modulus of f of xn minus f of xn minus 1 is smaller, the smaller f prime xi is in the neighborhood of the root. F of xn will be closer to f of xn minus 1, that is, the iterates are going to converge faster, the smaller is the value of the derivative f prime xi. If mod of f prime xi is less than 1 for all x in the neighborhood of the starting iterates x0 and x1, and this neighborhood includes the root, we can therefore be sure of convergence. This is true in cases 1 and 2 above, where f prime of x is always greater than 0 and less than 1 in case of case 1, and f prime of x is greater than minus 1 and less than 0 in case of case 2. Thus, we can see that in case 1 and case 2, f prime of xi, the mod of f prime of xi will always be less than 1. On the other hand, if the magnitude of the slope is greater than 1 near the root, that is, mod of f prime alpha is greater than 1, xn converges to alpha only in exceptional cases, no matter how close to alpha one chooses the starting point x0. For instance, in case 3 and case 4, even though we have actually started quite close to the root, you can see that we are moving away from the trial solution. This is because the slope at the root is greater than 1. The absolute value of the slope at the root is greater than 1. Thus, as we iterate, we move further and further away from the trial solution, while in case 1 and case 2, as we iterate, we move closer and closer to the trial solution. We can come up with a quick mathematical proof for this. This can be proved as follows. We can write x2 is equal to x1 plus x1 minus x0 times f prime of xi1, again according to the mean value theorem, provided xi1 lies between x0 and x1. Similarly, we can write x3 is equal to x2 plus x2 minus x1 times f prime of xi2, where xi2 lies between x1 and x2. Using the first equation in the second, we can write x3 in terms of x1, x0, and the derivatives at xi1 and xi2. Using the same idea, by induction, for any iterate, we can write the following. For instance, xn minus 1, we can write in terms of x1 and x0 according to this equation, to the first equation. Similarly, xn we can write in terms of x1 and x0 according to the second equation. Subtracting the first equation from the second equation, we get this equation. Xn minus 1 is equal to x1 minus x0 times f prime of xi n minus 1 times f prime of xi n minus 2 times up, which is a series extending up to f prime of xi1. Thus, we can see that if the magnitude of f prime of xi is less than 1 for all I, modulus of xn minus 1 becomes smaller and smaller for large values of n, and the iteration converges. F prime xi n minus 1 will be less than f prime xi n minus 2 times f prime xi n minus 3 up to f prime xi n minus 1, and so on and so forth. So as the As we add more and more terms, the right hand side becomes smaller and smaller and the left hand side converges. Next, let us consider two implementations of the above iterative scheme for calculating the square root of a positive real number c. That is, we want to find the roots of the equation x square is equal to c. We look at the first implementation where we write f of x as f of x is equal to half x plus c of x. The root obviously is alpha is equal to c of half, c to the power half. Also, it is clear that f prime of x, the derivative of f of x, is half minus c by 2x square. Therefore, at the root alpha, f prime of alpha is equal to 0. Hence, mod of f prime is less than 1 in a neighborhood of the root. Actually, it is 0 in a neighborhood of at the root, and at the neighborhood of the root, it has to be there must exist a neighborhood of the root where mod of f prime is less than 1, since f prime of x is a continuous function. For c is equal to 2 and with our starting guess of x0 is equal to 1.5, our iterative scheme converges in 2 to 3 iterations. We start with x0 is equal to 1.5, and by the time we reach iteration number 2, we can see that we are really close to the true solution, which is root 2, 1.414. On the other hand, if we consider the implementation B, in which case we write f of x is equal to c by x, for c is equal to 2 and x is equal to 1.5, our iterative scheme, which recall is xn minus 1 is equal to f of xn, which is equal to c by xn, gives x0 is equal to 1.5, x1 is equal to 1.3.3, x2 is equal to 1.5. So, it oscillates, right? The sequence does not converge. If one thinks of successive approximation or iteration as the numerical method adopted to find a numerical solution to the problem x square equal to 2, it is obvious that our choice of implementation, that is the algorithm, is crucial for the success of the method. The first implementation converged in 2 iterations, while the second implementation is never going to converge. This is true for numerical methods in general. Another commonly used technique in numerical methods is linear approximation. Here, we locally approximate a complicated function by its linear approximation. Suppose we wish to find the root of the equation f of x is equal to 0. Geometrically, this means finding x for which the curve y is equal to f of x intersects the x-axis. So, we start with our starting guess x0 and then use a numerical method, an algorithm, to try to reach the solution, which is where the red curve intersects the x-axis. The most well-known method for solving this problem, the Newton-Raphson method, consists of an iterative scheme where at each successive iteration we approximate the function y is equal to f of x by its tangent at that point and use that to find the next iterate. For instance, at x0 we have approximated the curve y is equal to f of x by the blue line being the tangent to the function y is equal to f of x at x0. Where the blue line meets the x-axis, That gives me my next iterate x1. So xn plus 1 I can write as xn plus f of xn divided by f prime of xn. The next iterate xn by plus 1 being the point where the linear approximation of the function y is equal to f of x given by the straight line passing through xn and f of xn with slope f prime of xn intersects the x-axis. The approximation of y is equal to f of x by its tangent at the point xn f of xn is equivalent to replacing the function with the first degree terms in its Taylor series about x is equal to xn. If instead of approximating the function locally by its tangent, we'd approximate it by the secant connecting two neighboring points on the curve, we have what is known as a secant method, which is another commonly used method for linear approximation of a nonlinear function. In the secant method, given the iterates xn and xn minus 1 as well as the function values f of xn and f of xn minus 1, we find the next iterate using the following update formula. At x is equal to xn plus 1, the local linear approximation to the curve y is equal to f of x intersects the x-axis. As you can see, we have tried to fit a line through the values of the function at iterate xn minus 1, which is f of xn minus 1, and xn, which is f of xn. And then where the line meets the x-axis, that is going to give me by next iterate xn plus 1. The third common numerical concept that we wish to talk about is the idea of recursion. Suppose we wish to solve numerically the differential equation dy dx is equal to f of xy with initial condition y0 is equal to p. According to the above equation, the slope of y changes from point to point. The simplest approximate solution to the problem discretizes the problem domain into equal sized increments of size h with function values y0, y1, y2 and ym corresponding to x values of h, 2h, 3h and nh. So at x is equal to 0, we have y is equal to y0. At x is equal to h, we have y equal to y1. At x is equal to 2h, we have y equal to y2 and so on and so forth. It is also assumed that the slope remains constant between the points, and the slope of the curve between n minus 1h and nh, for instance, is evaluated as yn plus 1 minus yn divided by h. Substituting this value of the slope in the differential equation, we have yn plus 1 minus yn divided by h is equal to f nh, which is the value of x, and yn, which is the value of y. We can rewrite this equation to yield the recursion formula. We can rewrite the previous equation by keeping yn plus 1 on the left hand side and moving the other terms to the right hand side. So yn plus 1 is equal to yn plus f of n of h yn times h. This is going to be true for all values of n. N is equal to 0, 1, 2 and so on and so forth. From this equation, you can see that each yn occurs first on the left hand side, then recurs on the right hand side of the equation. Hence, the above relation is called a recursion formula. So, if we know a starting value for y, if we know y0 for instance, using this recursion formula we can successively calculate y1, y2, y3 up to yn, and we can continue the recursion process until my recursion formula converges, that is until my value yn minus 1 becomes equal to yn. Iteration, linear approximation and recursion are methods which are used widely throughout the field of numerical analysis. Often, a numerical method may involve several iterative schemes, linear approximations, or recursions. However, the success of these schemes is measured in terms of their ability to come up with accurate and stable solutions. Accuracy and stability are two prerequisites of any successful numerical algorithm. In the following, we are going to talk about each of these concepts in greater detail. We will start with talking about the notion of stability, following which we will talk in greater detail about accuracy. What do we mean by numerical instability? If a numerical algorithm is unstable, small perturbations in the input data or in the intermediate computations can lead to gross errors. That is, they totally destroy the result of the computations. Perturbations on the input data can occur, for instance, due to minor errors in recording experimental results. If the input data to a numerical algorithm is experimental data and there are minor errors in the experiment, which are always likely, then if it is an unstable algorithm, those minor perturbations can give me totally erroneous results. Perturbations in the intermediate computations can occur due to numerical round-off resulting from finite precision arithmetic. Any computer, however sophisticated, only deals with that many numbers. So, any number can be, if a computer has accuracy up to t digits, it can only approximate a number using t digits. For instance, suppose we have to compute 4 by 3 at an intermediate step of a numerical algorithm, and our computer can only store 5 digits. In that case, 4 by 3 will be stored as 1.3333 and the remaining digits will be lost. If the numerical algorithm is unstable, the loss of the last digits may be enough to trigger an instability. Because of the instability, the numerical solution may differ widely from the true solution. The choice of algorithm is crucial in determining whether a numerical method will give stable results. Certain algorithms are inherently unstable. Others are stable for a certain range of input data, while still others are unconditionally stable. That is, they are stable for all ranges of input data. Suppose we wish to numerically integrate the following integral: yn equal to integral of x to the power n divided by x plus 5, and we wish to integrate within the limits 0 to 1 for values of n equal to 0, 1 through 8. We will solve this problem twice. Once using an inherently unstable algorithm, and the second time using a stable algorithm. For the first algorithm, we write yn plus 5 times yn minus 1 is equal to integral of xn plus 5x to the power n minus 1 divided by x plus 5. Recall that this is our integrand, so yn is this, yn minus 1 is equal to integral from 0 to 1 x to the power n minus 1 divided by x plus 5. So we can write this, and doing certain simplifications we can reduce it to 1 by n. If we perform this integration, it comes out as 1 by m. Thus we get the recursion formula yn plus 5 times yn minus 1 is equal to 1 by n. Using 3 decimals, the following are the results of our iteration. We start with y0, which we calculate accurately up to 3 decimal places, from which we get y0 is approximately equal to 1.82. Then using y0 in our recursion formula, we get y1 is equal to 1 minus 5 times y0, which comes out as 0.182. y2 can be written as half 1 by 2 minus 5 times y1, again according to our recursion formula, which gives me 0.050. y3 gives me 1 by 3 minus 5 times y2, which is 0.083, all being computed accurately up to 3 decimal places, and y4 gives me 0.165. As you can see, the answers are varying wildly. They are all over the map and are obviously wrong. The reason is as follows. Suppose the round-off error in the computation of y0, epsilon, is of the order 10 to the power minus 4, which is reasonable because we are using 3 significant digits in our computations. So the error in y0 is of the order of 10 to the power minus 4. In our second recursion relationship, this gets multiplied by minus 5 in the calculation of y1, because you can see there is 5 times y0. So whatever error there is in y0 gets multiplied by a factor of 5. Therefore y1 has an error of minus 5 epsilon. Similarly, y2 will have an error of 25 epsilon, because again we are multiplying y1 by a factor of 5. Thus the error gets scaled by a factor of 5 in every iteration. The error in y4 is as large as 625 times 5 times 10 to the power minus 4, which you recall was our initial error. The error in y4 is actually 0.3125. So you can see that the error has increased by at least 3 orders of magnitude. This is, however, note, is just the error propagating from the first iteration. Epsilon was the error in the first iteration. Additional errors accumulate due to additional round-off errors in each iteration, because in each iteration we are doing computations up to only 3 decimal places. Rapidly, the magnitude of the error soon equals the value of yn, and the results are practically useless. It is important to note that even if we decided to use more decimals in our algorithm, For instance, instead of using numbers with 3 decimals, if we use numbers with 5 or 6 decimals, we would still encounter the unstable behavior. The only difference would be that the instability would take longer, more iterations to manifest itself. That is, more iterations would be necessary to build up to a level where they lead to absurd results. Right? So this is not a problem of performing computations with too little precision. Right? It is the problem is the algorithm we have chosen is inherently unstable. The second algorithm we use is slightly different. In this case, we use a variation of our initial recursion formula, which you recall was this. Instead of using this recursion formula, we use the following recursion formula, where you can see the only difference is that we have divided both sides by, we have brought the 5 down to the denominator in the right hand side. But those two equations are identical. It's just that our recursion formula is different. If we use this algorithm, the error will be reduced by 5 in each step. However, we need a starting value ym. If we assume that the iteration very nearly converges after a certain number of increments, we can use the recursion formula to calculate the converged value. Assuming in this case that convergence has occurred after 10 iterations, so let's go back to our previous slide. So we are assuming that the iteration has converged in 10 iterations. So y9 is equal to 1 by 5 times 10 minus y10 by 5. Since we have assumed that the iteration has converged in 10 iterations, on the right hand side we can replace y10 by y9. The assumption being that y10 is almost exactly equal to y9, since the iteration has converged in 10 iterations. So we can write y9 is equal to 1 by 5 times 10, which is 1 by 50, minus y9 by 5, which gives me y9 is approximately equal to 0.017. Again, notice that we are performing our computations only for up to 3 decimal places, right? We have not increased the accuracy of our computations. Similarly, using the same recursion formula, we get y8 is approximately equal to 0.019, y7 is approximately equal to 0.021, y6 is 0.025. Eventually at y0 we get 0.182, which is the exact solution for this problem. Although the numerical computations have been performed up to 3 decimal places as in the first algorithm, in this case the stability of the algorithm does not allow round-off errors, that is numerical perturbations, to swamp the solution and give totally erroneous results. As should be clear from our discussion, the stability of numerical algorithm is crucial to a numerical method's ability to give results that do not vary arbitrarily with minor changes in input data or due to the accumulation of round-off. However, in addition to giving stable results, it is also desirable the results of a numerical algorithm be accurate. Thus, apart from stability, accuracy is the other important criteria that determines the suitability of a numerical algorithm. In other words, the errors which measure the deviation of the results obtained using a numerical algorithm from the exact or true solution of a problem must be as small as possible. This can be analyzed through what is known as error analysis. In the next lecture in the series, we are going to talk in greater detail about error analysis, since error and stability are the two criteria which determine the effectiveness of a numerical algorithm. Thank you.